Thanks everyone for being here. So today I'm going to be talking about a recent paper of ours, Directions of Curvature as an Explanation for Loss of Plasticity. There's a lot to unpack in this title, so let me just get started. Loss of plasticity, briefly described as this reduction in learning ability. It's a phenomenon specific to neural networks where a neural network's ability to learn is progressively diminished when faced with a continually changing stream of experience. And while it's empirically observed in certain cases, it remains somewhat mysterious. For example, what determines learning ability? Why is learning ability reduced? And so the question we set out to answer is, what is loss of plasticity really? And so I'll give a brief overview of this talk. There's going to be 3 sections. The first is going to be evaluating previous explanations for loss of plasticity. Afterwards, I'll be proposing, this curvature perspective on loss of plasticity that you may have inferred from the title. And then lastly, if we have time, I'll say a little bit about how this curvature perspective may motivate regularization as a means of preserving plasticity. I should also say, if you have minor clarification questions throughout the talk, feel free to raise your hand. Hopefully I see you. And between the transitions of the sections, I'll take a look around to see if anyone has any questions. Okay, so evaluating previous explanations. I'm going to just jump right into this problem setup. So we're going to be looking at a sequence of linearly separable MNIST classification problems. Linearly separable means a linear classifier does quite well in this problem. And it's a sequence of problems, so there's a task that changes. How does this task change? Well, in each task, we're going to have a random assignment of labels on these images. And these label assignments are completely random. So for example, you can see that this 7 has a label of 2, and this 7 over here has a label of 7. And so the task for 200 epochs is to memorize all these labels. After 200 epochs, the task changes. There's a new assignment of random labels. And so some get reassigned, some probability, and others, and so some can change and some don't. Most will change. And again, the neural network needs to memorize all these random labels for within 200 epochs, and this continues. And so because the labels keep changing, you need to keep learning. And also, because any random label assignment is about equally difficult, we would expect the performance at the end of each task to be roughly consistent or roughly constant. Yes?
There's a set of instances, but they just, you only have 200 epochs. You see the entire set of instances?
200 times.
200.
Yeah.
Okay.
Yes. Yeah, so there's only maybe 10 images shown here. We're actually looking at maybe 1280, so 1,200 roughly image observations, and we're randomly sampling them with a mini batch of 128. Yes, Russ?
We use the phrase memorize as image. Are you trying to generalize from them or just really memorize?
This is, only about training accuracy and trainability and training,
No, thank you.
Yeah, no generalization yet. Okay, so what do the learning curves on these sequences of tasks look like? So you can see initially a neural network with ReLU activations can learn a solution that's better than linear, and it does so more quickly. But by about task 5, the ReLU network is about on par with the linear network. And as training progresses, as more tasks are encountered, the ability for the ReLU network to learn within that 200 epochs diminishes. And so there's a lot going on in this graph, right? There's a learning curve for each task for different activation functions. There's a lot going on. So let me just summarize it. Instead of looking at the learning curve entirely, I'm just going to plot the accuracy at the end of the task. And I'm going to be having that on the right axis. And you could think of this almost like Chekhov's axis. If you see one on the right, you should expect one on the left. And so what I'm really interested in is explanations for loss of plasticity. So for the linear function approximator, although loss of plasticity doesn't occur, the accuracy stays constant. And so we would hope that an explanation is also constant. It doesn't vary in the same way as when loss of plasticity does occur. So for the ReLU network, when loss of plasticity does occur, the accuracy goes down. And we would hope that the explanatory metric captures this by decreasing as well. I've arranged it so that the explanation is always decreasing if loss of plasticity occurs. So we're trying to see this kind of consistent trend. If loss of plasticity doesn't occur, we don't want any change in the explanatory metric. Otherwise, we want to capture the trend. Okay. Yes?
So is this just like one hidden layer of
this is 2 hidden layers, yeah. Yes.
I assume you're not saying that this would be true for any regular. This was just for the setup you used, right?
Yeah, there are some specifics to the setup and the problem, and there's some nuance to it. Maybe we can talk about it afterwards. So I've been using the term explanation a lot, and I realize it can be a little bit confusing. I don't mean like a causal explanation. I'm talking about why or what is loss of plasticity, not like why does loss of plasticity occur. And so I had a hard time articulating this point before, and I thought maybe a good way to describe it is by asking OpenAI's DALL-E to give an illustration of the allegory of the cave in the style of Dune. So in the allegory of the cave, if you're not familiar, Plato describes a person who has spent their whole life in a cave staring at a blank wall, and they see shadows on this wall. But they have no conception of what a shadow is or what a light is. All they know is these shadows appearing on the wall. So what we're trying to describe in the context of loss of plasticity is what this shadow is, not necessarily why does this shadow occur, what occurs. We're not trying to explain what occurs in the outside world to give rise to the shadows, but just point out the fact that these things that we see on the wall are actually shadows, just to give a more complete description of what the phenomenon of loss of plasticity is. So let's continue with the setup. I've described a little bit about the problem, a little bit about these explanations. So what I'm going to be doing is training this feed-forward neural network with 2 hidden layers with Adam. And so Adam is an optimizer. It's not quite dependent on the choice of optimizer. It also occurs with SGD and other variants, but I'm just going to focus on Adam because that's what's used most in practice. And I'm going to be comparing those learning curves and the explanations for these learning curves under 3 different activation functions. And again, I'm going to be evaluating it with the training accuracy at the end of each task. So what are these 3 previous explanations? I'll go through each one in turn. First, and maybe most obvious, is the weight change. So loss of plasticity might be explained by the fact that the weight change is decreasing. So for example, if the weight change were to go to 0, then your weights are no longer changing, you're no longer learning, clearly you've lost plasticity. So the explanatory metric I'm going to be plotting on the left y-axis is the average weight change within a task. So for a ReLU network, it is a pretty good explanation, right? The accuracy goes down as more tasks are encountered. The weight change also goes down for the ReLU network. So we might expect that this is a reasonable explanation. But for leaky ReLU, it's not the case. Actually, for leaky ReLU, the weight change doesn't decrease, it increases. So this explanation doesn't seem to be consistent with the finding of loss of plasticity. The second potential explanation is maybe there is some lack of diversity in the features being learned. By features, I mean the penultimate outputs of this neural network before the last linear weight matrix is applied. So if the normalized rank of the feature matrix decreases, that means there is less features being represented by the neural network. And so maybe this is a good explanation for loss of plasticity. Again, for the ReLU network, yeah, it seems like a pretty reasonable choice. But in this problem, TANH actually doesn't lose plasticity, and yet there's a decrease in the feature rank learned by the TANH network. So again, doesn't seem like feature rank is an explanation for this. The last one that I'll cover for now is neuron dormancy, also like referred to as dead units. Yes, Kalarina?
I thought in your first explanation of like a possible loss of plasticity, you had ReLU and leaky ReLU.
Yeah.
But here you have ReLU and TANH. Is that a reason why you didn't use leaky ReLU?
No. So I've run the experiments for all 3 activations, and I have all these like metrics logged. I'm only showing 2 at a time to show a single counterexample. If I have one that doesn't follow the trend, then it's not a really good explanation. Yes, Fernando.
Have you tried more number of tasks? Because at least in the experiments that I've seen before, it's like thousands, maybe hundreds of tasks before some of the networks lose plasticity. So maybe the TANH network is about to lose plasticity, and the explanation is just preceding that, and then later is what you're going to see the growth.
Yeah, Fernando has a lot of experience with loss of plasticity, and you're right, actually. So there are some peculiarities. In this setup, TANH doesn't lose plasticity, but that is enough to rule out the feature rank as an explanation, I'd argue. And yes, if you're to run this for much longer, TANH actually eventually loses plasticity. But it's still kind of interesting that TANH takes so much longer. And maybe it's not a coincidence that TANH is kind of often used in reinforcement learning. I have some thoughts on that. Maybe we can talk about it at the end. So where was I? Yes. So the third explanation I'm going to be going over is neuron dormancy or dead units. And so with ReLU networks, it's kind of easy to know what a dead unit is, right? Like if it's 0, if the ReLU activation is 0 all the time, then it's never active. It doesn't contribute to the output of the neural network. For something like leaky ReLU or TANH, it's a little less clear to think about it that way. So what I'm going to be measuring instead is the entropy of the hidden activations. If the entropy is very small, that means the activations concentrate on specific units, and others are, in comparison, quite small. Okay, so again, for ReLU, yeah, it looks great. Neuron dormancy is a great explanation for loss of plasticity, but again, leaky ReLU kind of throws a wrench into things. Although initially there's a bit of a decrease, loss of plasticity doesn't occur for leaky ReLU, and then actually dormancy, the dormancy that occurred gets, I guess, reversed. Yes, Shivansh?
How do you measure dormancy for leaky ReLU?
Yeah, so that's why I described the fact that what we're actually looking at is the entropy of the hidden activations. So this is, if the entropy is very small, that means all the activations are in like particular units. If the entropy is very large, that means all the activations are roughly like equally large in magnitude. So it roughly captures what we mean by like a dead unit in this relative sense. Okay, so I've presented 3 explanations and 3 counterexamples to those explanations. And so what's the takeaway? Either loss of plasticity is like not just one thing, but many different interacting things depending on the activation function and the structure of the neural network and maybe the problem. Or, and maybe the title kind of give it away, there is a single underlying explanation that we missed. And so this is what I'm going to be spending the next section talking about. I'll just pause for a second, have some water.
Oh, sorry, you quickly remind us what were the 3 reasons?
They're not so important, but weight change, which is kind of proportional to gradient magnitude, feature rank, so the diversity of the features that you learned, and neuron dormancy, which is kind of like the diversity of the activations in the neural network. Okay, so what's missing in these previous explanations? Gradient vectors seem to encode a lot of important information for learning, but gradients are vectors, so they have a magnitude, and we saw that the magnitude doesn't really explain loss of plasticity because the weight change wasn't really reflective of didn't explain loss of plasticity. But again, a gradient is a vector, so not only does it have a magnitude, it also has a direction. So maybe loss of plasticity has something to do with gradient directions. Some intuition for why gradient directions might matter is as follows. Maybe loss of plasticity in neural networks occurs due to a reduction in gradient diversity. So I'm going to kind of sketch it out with this diagram. Early on, at the beginning of, say, the first task with a randomly initialized neural network, we have stochastic gradients, and they point in all sorts of directions. Some go left, some go right, some go up or forward. And because the gradients are pointing in all sorts of directions, it's quite easy to like navigate the optimization landscape. But as training progresses, if these gradients were to point in more and more similar directions, it takes longer to move in certain directions. So for example, if there's a minimum to the left of this point, at initialization, all we need to do is take that one gradient, stochastic gradient, if we're lucky, in the left direction. As training progresses and these directions concentrate, we have to take these longer winding paths to move, say, to the left or to the right of where we started. This is just an intuition. This is not exactly how stochastic gradient descent works. First of all, there's like many directions, and the kind of concept of geometry gets a little tricky to think about. But this is kind of what we're working with for the intuition. So how would we measure this gradient diversity that I'm referring to? Well, let's review some calculus. So we can talk about the local curvature at a particular point with a Hessian matrix. So the Hessian matrix is this matrix of second-order derivatives of an objective function j. And the objective function depends on theta, the parameters or weights of your neural network, but it also depends on the data from task t. That's why t is involved in h and j. The Hessian rank, so the rank of this matrix, counts the number of gradient directions of curvature. So if the rank is full, that means any direction that you move from theta, given the data from task t, either curves upward or downward. If the Hessian rank isn't full, that means So there are some entries in the Hessian matrix which are linearly dependent on other entries. And what this means is that there is a direction that is flat. If you were to move in it, your loss doesn't change. So my claim is that the Hessian rank actually captures the idea of gradient diversity that I outlined on the previous slide. This may seem a little strange, so let me work up to it. I'll first say that actually the rank is expensive to calculate. We're looking at a Hessian matrix, a matrix which is d by d, and to calculate an SVD of this matrix, which is needed for the rank, it requires something on the order of cubic in the number of your parameters. Even for something like MNIST, like a neural network on MNIST, or even a linear approximator on MNIST, this can be pretty costly. And so we're going to be using this empirical Fisher approximation. So it's a kind of a fancy term for saying that we're going to approximate the Hessian with the outer product of this gradient matrix G, where each entry of G, so Gi to Gm, are stochastic gradients for a single data point. And I'll make 3 observations. So first, this outer product of G is kind of like a stochastic gradient covariance, or maybe more precisely like the second moment of the stochastic gradient. The other observation is actually by the properties of like this type of outer product approximation, the rank of G transpose is the same as the rank of G transpose G. And this is great because we reduce the SVD computation complexity from d cubed to m cubed, where m is the number of samples that we're using to approximate this. If we have a batch size of 128, this becomes somewhat reasonable. And the last thing is that, well, if this rank approximates the number of directions, and this approximation is approximately this stochastic gradient covariance, what this rank is actually also telling us is about the number of ways that the stochastic gradient can vary. So if the rank is small, the stochastic gradient can't vary very much, and so the directions concentrate in a similar sense as I outlined in 2 slides ago. Okay. So let's evaluate the hypothesis that loss of plasticity is explained by the fact that fewer directions of curvature are present at the beginning of a task. So again, by intuition, less gradient diversity at the beginning of a new task. And the explanatory metric here is this approximate Hessian rank. So the rank of that inner product of stochastic gradient matrix.
Oh, what's the relation between true Hessian rank and this approximate Hessian rank?
I have in the paper an evaluation for how well it approximates it, and I have a figure at the very end. It's hard to evaluate because to know how well it approximates it, I need to know the rank of the Hessian. And if I can't calculate the rank of the Hessian, it's hard to evaluate. So it's in a small setting, it is actually more accurate than other approximations to the Hessian, specifically for this rank calculation. So there is good reason to believe that it is capturing what we think it is.
Do you know if it under approximates, overestimates?
It's at the beginning, it tends to underestimate the rank, and towards the end, it tends to overestimate the rank. I don't have a figure for that in the paper. Yeah. Okay, so I'm going to be plotting the explanation versus the accuracy on 3 activation functions in sequence. So first, we're going to start with our good old friend ReLU. So ReLU, as we know, loses plasticity, and for this metric, this explanation, the Hessian rank, it also decreases. And I'll also note that loss of plasticity occurs maybe slightly before task 5, maybe task 4, but maybe starting at task 2, we already see a decrease in the Hessian rank. So again, I'm not claiming anything causal yet, but it seems to hint at some causal explanation. Next, let's add the line for leaky ReLU. So leaky ReLU loses plasticity a little bit later, and so the Hessian rank starts decreasing a little later. And again, the decrease precedes loss of plasticity. So again, maybe hinting at some causality, but I'm not claiming anything. And then, yes. And then finally, for the tanh, at least on this number of tasks, we don't see loss of plasticity, and we don't see any movement in the Hessian rank. So in comparison to the 3 explanations I provided earlier, this seems to actually be rather consistent with the findings on this relatively small simple MNIST problem. Does this generalize to other problems? I'm just going to flash a bunch of results at you. Yeah, it does. There are some interesting dynamics, for example, on the random label MNIST. So this is on the full data set. Actually, although there's an initial large decrease in the Hessian rank, it seems to try to recover. I'm still trying to understand what's going on here. But in general, as on the range of when loss of plasticity is occurring, we do see that the Hessian rank coincides or precedes loss of plasticity. Reduction of the Hessian rank precedes it.
So what? Rank precedes loss of plasticity.
Yeah, so the main claim is that reduction in the Hessian rank coincides with loss of plasticity. And
Loss of plasticity is essential.
Yes. Yeah. If you have more questions about those results, we can cover it later. Am I doing on time? Okay, so I'm going to be talking lastly a little bit about preserving plasticity with regularization. And first, I'm going to appeal to some intuition from linear regression on the connections between regularization and curvature. So in linear regression, L2 regularization is sometimes used to increase the rank of a Hessian. And in linear regression, the Hessian is just XTX. So in linear regression, we're trying to minimize a mean squared error. The solution to this optimization problem is XTX inverse XTY. XTX is the Hessian. If the Hessian is low rank or not full rank, we can't take this inverse. It's not well defined. So one of the motivations for introducing L2 regularization is that if we were to add this L2 regularizer, so in addition to the mean squared error, we're also going to add a penalty term for the size of these weights. If we were to do that, then the solution becomes, the solution involves this matrix, which is XTX, which could be low rank, plus a diagonal matrix of identity scaled by the regularization strength. And now suddenly we can take this inverse. And so although originally we can't actually solve this mean squared error problem exactly, with regularization we can by improving the conditioning of the Hessian matrix. So maybe we can extend this motivation to this finding about Hessian rank, that maybe regularization also improves the Hessian rank in neural networks, and thereby maybe preserving plasticity. So this is the intuition. Let's get into a little bit more specifics on some previous work. So we know that plasticity and curvature is present in initialization. We have a randomly initialized neural network. We see that it has high Hessian rank. We see that it's able to fit the task. It has plasticity and it has curvature in the sense that I defined before. So the idea is maybe we can regularize towards the initialization in some way and thereby preserving plasticity by keeping ourselves close to that initialization. So some previous work added a slight modification to traditional L2 regularization, where instead of regularizing towards regularizing the magnitude of your weights or your parameters, instead you're going to be regularizing the distance between the parameters at time t for, let's say, layer L and index I, versus the parameters at initialization when t is equal to 0. So what this means is that you have a neural network, you randomly initialize, you save those weights, you hold them in your back pocket, and then every time you do an update, you compare whether the distance, if the distance moves very far from that initialization, you'll kind of try and keep it close. So in the context of classification, you just add this hyperparameter scaled of this regularizer to the objective, and perhaps you'll be able to preserve plasticity. I'll just make one note that this regularizer can prevent parameters moving very far from initialization, and this could be problematic if you need your parameters to be large to fit a particular task. So our idea is a slight modification of this regenerative regularizer. There are some nuances that I can explain, but I will just briefly state that all that we're doing is changing the types of differences that we're making. We're not taking the difference between a parameter value and its parameter value at initialization. What we're doing is we're sorting the parameters at initialization, and we're sorting the parameters at any time t, and we're comparing not the difference between the specific values, but in the order of the values. So you take the smallest value you had at initialization, the smallest value you have at a particular point in time t, and you take that difference. Why would you do this? It seems kind of strange, right? Well, actually, this term, Wasserstein, is not like I didn't pull out of nowhere. It's actually, the reason for doing this is that what we're actually comparing is not the L2 distance between these parameter vectors, but actually the distributional distance between the empirical distribution at initialization and the empirical distribution of your parameters later on in training. So that point is somewhat relevant to the motivation for this. It is a distance between distributions. But there's another property that might be a bit more down to earth. So we're taking the difference in these order statistics, and because we're looking at the difference between like the smallest values and the second smallest values and the third smallest values, that is actually the smallest difference you can take between two lists. I don't have a proof for it here, but like if you were to take like any like list, sort it, and take the difference, it's always going to be smaller than any other arbitrary ordering. So the Wasserstein regularizer is a lower bound for the regenerative regularizer. It's weaker in a sense. For any regularization strength that the regenerative regularizer imposes, the Wasserstein regularizer will have a smaller strength. So I'm going to evaluate these regularizers against an unregularized neural network on a slightly different problem, CFAR10. And so in CFAR10, the images are RGB. Unlike MNIST, which is like black and white, we have a bit more structure. The classes are a little bit more interesting. I think I have an image of that. Let me just skip to it really quickly. Right? We might have like a ship, a horse. There's like a frog here and there, and a bird. But we're still doing this like label memorization problem. We're taking all these complicated images, assigning them random labels, and asking, in this case, a ResNet, like this big convolutional neural network, to memorize all these labels. So ResNets are a lot bigger than the neural networks that I was looking at in the previous problem on MNIST. It has like something like 18 layers, batch normalization, skip connections, convolutional layers, all sorts of things that weren't present in those feed-forward neural networks. And so we're going to be looking at how these regularizers impact our ability to learn this complicated memorization problem on CFAR10. And we're going to have a baseline, just the unregularized objective. If you're just train a ResNet on this problem, what would that look like? So first, I want to evaluate whether regularization actually preserves curvature in the sense that, because this was the whole motivating pitch for why regularization might have anything to do with plasticity. So if we were to train the neural network without any regularization, this is unregularized, we actually have an increase in the Hessian rank compared to early on with the regularized. It goes from maybe about 80%, having 80% of your directions of curvature up to 90% with the unregularized objective. But over time, as more tasks are encountered, this rank actually decreases for the unregularized setting. For the Wasserstein and regenerative regularizer, it's not able to get its Hessian rank as high, but it's able to maintain at least some of its Hessian rank over the period of like 50 tasks. So, okay, this Hessian rank preservation thing seems to make sense, but does this have anything to do with loss of plasticity? Yes, Mike.
I thought we showed the Hessian rank before you started talking about regularization. I thought you showed that it started high at initialization. And now suddenly, even the unregularized one, which I thought would have been the curve you showed before, now it seems like it starts low at initialization.
Yeah, I noticed that too. So what this point is actually is not the Hessian rank at the begin.
That's the first round, first task of training.
Yeah.
Okay.
Yeah, thanks for that.
Oh, I just have one more question.
Yeah.
So, do we always want a high Hessian rank? Like, does that mean if we have a high Hessian rank, that means we're going to, even in like a non-continual setting, even if we want to learn in one task, do we always want high Hessian rank?
I would say yes, and I have like a project that is kind of investigating ways in which we can do this without regularization, and it seems to be quite promising. Yeah, there is some nuance to this because what I'm talking about when I talk about the Hessian rank, I'm talking about the Hessian rank at the beginning of a task. Like at initialization, if you have new data you've never seen before and you need to learn on it, yeah, you want a high Hessian rank. But what tends to happen is if you look at the Hessian rank at the end of a task, like near a local optimum, it tends to be low. And that kind of makes sense because as you train on this like high dimensional loss landscape, as you approach a local minimum, more directions tend to be flat, or at least relatively smaller than other directions in magnitude. And so whether we want to decrease through training or not, I is less certain, but we definitely would want it at the beginning of a task to have a high Hessian rank. And maybe to return to your question, Mike, so why is this so low? This is a residual network with batch normalization, and I think the batch normalization has something to do with it. Yeah.
Oh, sorry. I guess related to that question, but wouldn't the Wasserstein or the regenerated also have, shouldn't that also preserve higher rank than unregularized? So what happened there?
Yeah. Well, so this is a Hessian rank. So it's the Hessian of the unregularized objective still. I'm adding a regularizer, but the Hessian rank is still with respect to the unregularized objective. So the regularizer kind of prevents you from deviating far from initialization. And if at initialization your Hessian rank was like so small, then perhaps it's kind of preventing the Hessian rank from growing in the same way in this residual network. If that makes sense. This, in a couple slides, there's another smattering of results in other domains, and this is more specific to ResNets. Yes?
Ensuring that the weights are not. That's why we have the.
Sorry, could you say that again?
When we are regularizing the integration, we are ensuring that the weights are not good.
Yeah, it does prevent the weights from growing.
Here we are comparing with the initialization. We are ensuring that the weights do not change much from the initialization. So is the reason why
So in a couple slides, I will show that yes, the regularizers prevent the parameters from moving far from initialization, but this figure doesn't show that yet. This is only about the curvature of this landscape at initialization. It has nothing to do with the distances yet.
is the reason why we chose this regulation instead of the usual just L2
Oh, as opposed to like weight decay or just L2 regularization. Yeah, so I do have results with L2 and weight decay on one of the problems, the simplest one, MNIST, and it does the worst and is the most hyperparameter sensitive, so I just decided to focus on the more performant regularizers in this set of results. But you're right, weight decay or L2 regularization would have a similar effect, it's just more difficult to tune.
regarding the change in his hit. So when we're calculating his hit, are we just calculating all the parameters of the network or just the final?
Yeah, early work, I tried approximating with just the last two layers, for example, because those are, those aren't that many parameters. It's reasonable to do. For this work, this is with all the parameters. And so for the ResNet, there's something like, I don't know, 18 million parameters or something, which seems huge. But because we're doing this approximation with like the outer product of gradients, the matrix that we get in the end has dimensionality of like the number of input examples I'm looking at, not the parameters. There is like a matrix prior to that I multiply, which is like the number of examples times the number of parameters. That is kind of large, but it's reasonable for at least ResNet 18.
So if we are calculating his hit across all the parameters of the network, I would argue that maybe we don't need like after a point, the initial part of the network just learn how to get features from the images, and only the changes are only in the last layers where we are taking the classification.
Yeah, that's a great point. So that would be the case if we were like respecting the class assignments, but this is a complete random assignment of labels.
But it makes it the same. So the
Yes.
features will be the same. Feature extraction will be the same.
Let me go to this picture, for example. So this, although you can't really make it out, CFAR10 is kind of funny. This is a frog. This is also a frog. This is a frog with a label of 8, and this is a frog with a label of 2. Knowing that they're both frogs isn't going to help you classify them. because they have completely different labels. It actually makes it more difficult because maybe these are kind of close in like color pixel space, and you need to separate them based off of some random features that you realize about these two images of frogs to say that this is a 8 frog, and this is a 2 frog, and this is the 4 truck. Like,
That two frogs, just like that two, that two.
yeah, exactly. This 2 frog is the same as the 2 shit. So it is, the features don't have structure for you to leverage in this problem. Yeah. It is weird. I give you that.
You made it.
It's what people used to evaluate. The reason is loss of plasticity happens a lot quicker with these like memorization problems, and it just is easier to iterate quickly on. Okay, keep going then. So this is about the Hessian rank. I didn't really show any curves yet. So what does the accuracy look like? So the unregularized ResNet is actually able to increase its accuracy, training accuracy, up to about 100%. So it's able to perfectly fit the data within maybe 10 tasks, but this ability actually doesn't persist. After maybe about 20 tasks, the training accuracy starts to go down. So the unregularized ResNet actually is losing plasticity. And the two regularizers, Wasserstein and regenerative regularization, are not suffering from that problem, but there's a little bit of a performance gap, right? Both the Wasserstein and regenerative regularizer are able to maintain their performance and eventually do better than the unregularized case, but they aren't able to perfectly fit the data. If we gave maybe more epochs for memorization, it would be able to memorize labels completely, but it isn't within 20 epochs. Yes?
I assume with these regularizations, you have some regularization weight parameter.
Yes.
Presumably regen, you could tune it down and it would start to look more like regularized. So like, what is that gap and how did you tune that parameter?
Yeah, there's a grid search done for both these independently.
What did you optimize with that grid search? Were you optimizing area and curve, or were you optimizing ending performance?
It was ending performance. And so there was a regularization strength for regenerative and Wasserstein. And in the paper, there's a small ablation on like the regularizer strengths. The Wasserstein regularizer is a little less sensitive to the regularization strength, only because it's like smaller. Yeah. Yes.
Or the regularized version just have really tight intervals, or?
Yeah, they're pretty small. You can even see as loss of plasticity occurs, you actually have more variance. But initially, this is a supervised learning problem. The error bars tend to be quite small in supervised learning, especially image classification. Yes?
Isn't the computational complexity of the one you're proposing LON?
Yeah, it is. And that can sound annoying, and it is a little bit. It is, an extra sort, which you'd want to get away from. I would argue that it doesn't have to be so bad. You don't have to sort literally every iteration. The parameters don't change that much in their ordering. So you can look at sorting less frequently. I think in this case, I'm actually sorting maybe every 4 iterations, and I've experimented with 10 and 100. But you're right, that is a downside. Computational complexity.
Almost worth it. The complexity.
Yeah, there are like approximate sort algorithms or sorting algorithms specific to like nearly sorted lists. I'm using just the default sort, so I'm actually not taking advantage of that, but you could potentially. Okay. So I claimed earlier that, hey, maybe the Wasserstein regularizer is good because it allows the parameters moving further from the initialization, and sure enough, that is the case. If you don't regularize, your distance from the initialization just kind of grows, maybe without bound. We'd have to run this for a little bit longer to see. For the Wasserstein regularizer, you're able to almost move an order of magnitude further from the initialization. And I think the regularization strengths found for these, the optimal regularization strength found for these is the same. So I think it's something like 0.001 or 0.0005 or something. With the same regularization strength, we're just able to move further from initialization and perhaps make more use of that ResNet capacity.
I have a question
Yeah.
about the previous slide.
Sure.
So it looks like even after actually never mind. I just realized if you train for 200 epochs, the accuracy is just 20%, or below 20. Because I was just wondering, because it sounds like the computation cost is very high. What if I just reinitialize and just retrain without the extra cost, right?
Yeah.
But I think it's that
That's a
answer.
reasonable question. Now that I think about it, you have random labels, right? Like, no matter how good you were on the previous task, on the next task you'll probably be worse than random. I don't know. Seems like it.
In the paper, actually, I don't talk about accuracy. I talk about the objective being minimized. And what tends to be the case is at initialization, you have some error on the first task. And you learn on that first task, then you begin the second task. And the error is actually much higher. It's higher than what you initialize. So you learn something, and that doesn't help you on the next task. It tends to hurt.
You have to unlearn it.
You have to unlearn. Yeah.
Somehow you've learned super fast because it takes like 5 tasks or 1,000 epochs, 5 times 200 to reach a performance of 80%.
Yeah. So I think this first data point is actually before any training has been done. So this is initialization before training on the first task. So I think it actually starts maybe around 70, 85%, and it does increase afterward. And actually, it's interesting that this ResNet is one of the architectures that I looked at that is actually able to increase its performance over the first couple tasks. The other networks either maintain some constant level performance or decrease over time. And that is kind of surprising because there's no structure between the tasks. So it's not really clear what the neural network is learning that helps it make progress on new tasks. Some thoughts, but nothing concrete yet.
Do you also know how, like maybe initial layers, they don't change much, right, across tasks?
I haven't looked too much at the specific differences in layers, but it is interesting, maybe.
You finished up.
Yes. Okay, so yeah, this is result generalized. Generally, yes. We generally see that loss of plasticity doesn't really occur. We have relatively low errors between both regularizers, and both are able to maintain this Hessian rank. So conclusion and next steps. It seems like the Hessian rank is a consistent explanation for loss of plasticity. And it would be really good to extend this finding to something more causal. What causes the Hessian rank to decrease, or what causes loss of plasticity to occur? This would give a lot more insight into what these learning algorithms are really doing. And some progress is being made here, and maybe I'll have something to say in June. It was kind of alluded to a couple times that do we want a high Hessian rank, or what about generalization? And I'll just comment that flatness seems to maybe help generalization, especially near a local minimum. So is there a potential trade-off between plasticity and generalization? If you have highly plastic algorithms, are you sacrificing something? No, too early to say. Extensions to reinforcement learning I've given some thought to. It, in some sense, is a non-stationary problem. Value estimation is a sequence of regression problems, depending on the targets being changed or the policy being changed, the data distribution shifts. So reinforcement learning, extending these results to reinforcement learning is pretty interesting to me. And then lastly, I want to comment regularization was kind of used as a lever to understand loss of plasticity a bit better, but I actually don't really think that everyone should drop everything and regularize all your neural networks or anything. I do want to think beyond regularization, specifically because it's hyperparameter dependent. And in continual learning, this hyperparameter dependency is particularly annoying. I don't know what my data is going to look like, so I don't know what kind of hyperparameter I should set. It also may limit scaling, as we saw, we aren't really able to make the most use out of the ResNet capacity within the same number of epochs as an unregularized objective. And then the big picture is, I think we need to understand the dynamics of learning algorithms, understand how the real world casts this shadow of loss of plasticity in order to scale these learning algorithms towards continual learning. And before I finish, I'll just like to thank my collaborators. So Haruto is a master's student at the U of A with Rupam. Dale and Marlos are my co-supervisors, and this is a QR code and paper link if you're interested. Thanks. Yes, Adam?
What are you hiding from us?
Slide 47.
Oh. I just threw some extra results, yeah.
None of our business.
Yeah. If people ask. Yes, Russ.
So, as you point out, this is just trying to memorize. I want to generalize. I want to actually go beyond the examples I've seen. Do these results still apply, or is this regularization has a role there also, right?
Yeah, that's a great question. So I kind of skipped over some of the results, but in not all the problems that I looked at are label memorization problems. Some of them are like label shuffling. So it respects the class identity of observations and assigns all the frogs to ships and all the ships to, I don't know, birds. And there you can look at generalization. I haven't personally like investigated the generalization question too much, but I have seen a little bit here and there in my experiments that you do tend to see generalization performance suffer alongside loss of plasticity, but I wouldn't say anything more concrete about it yet.
The follow-up is, I mean, I think the rule is sort of being constant. Now, obviously, I'm naive in that sense. But I think the rule changes dramatically from second to second. Just small changes, does this idea still apply?
Yeah, again, returning to that like label shuffling thing, the non-stationary is like less severe in some sense, in a way that I'm trying to understand how to measure, but I haven't yet. And if it does change slower, loss of plasticity occurs slower, but it still does occur. This is to run it for not like 50 or 100 tasks, but like 1,000 tasks. And what I'm interested in right now is like understanding like the really large scale behavior of continuing learning after like thousands or tens of thousands of tasks. But yeah.
Well, I got prime data.
Yeah. Yes.
I think this is related to Rafi's question. The current change of the task is conflicting to each other. So you are shuffling the label, so you are randomly assigning the label. But in reality, most of the field learning is we are adding new knowledge.
Mm.
Or maybe the change is random. Maybe you can try something like say Siva 100 and you can take 2 classes out.
Yeah.
And I can gradually learn more and more. It's not usually the performance will be and why people haven't
Well, so Shibansh has a paper that did almost exactly that. It's like the task incremental setting. I haven't did it yet, but I guess I will have to for some rebuttal in the next week or so. Yeah.
Yeah, okay.
Sure.
Yeah. There's a lot of like problem levers you can change to make it more severe or less severe. And it just so happens that we've designed like our systems, all our machine learning systems, in the regime where it occurs very slowly, and so we don't encounter it in practice. But yeah, I mean, we've kind of created this culture, and we've ignored these other problems, which are becoming increasingly important. The label memorization thing is just like the worst case scenario. Yes, Callie?
Yeah, were like the benchmarks that you use, so those like, is there like a common set of benchmarks that I remember in his talk yesterday? It was completely different. So like, I imagine in like Shibansh's paper, he showed that my thing works, and I like fixed loss of plasticity, but they're like, oh no, JK, you didn't. So like, was it because it was a different problem setting, or like, yeah?
I'm not commenting too much about solution methods.
Yeah.
So there are many ways to mitigate loss of plasticity, and Shibansh was actually kind of maybe the first to like kind of point out this problem. Before 2020, if you like go on Google Scholar and search a date range, before 2020, quote loss of plasticity, quote neural network, it's only biology papers. So like no one has really looked at the prior. And so yeah, there are solutions like backprop that help mitigate this.
This is an
And-
example of that phenomenon, right?
Yeah.
The fact that the Google Scholar changed.
Yeah. And then the problems, some of them in Shibansh's paper were like the permuted MNIST, for example. That's one of the problem settings that I was looking into. The label memorization problem is just, I think, the cleanest, quickest depiction of the phenomenon. And then I guess Fernando has worked on like the problem at scale. And so that's like very important too, and not, I guess, the scale of experiments that I've conducted. Yeah.
About the first part presentation explaining the loss of plasticity. How sure are you that the cause of loss of plasticity is a loss of diversity of variance, and there is no other cause for both of these others? For example, the number of active nodes. Because as far as I understood, the only proof for this reasoning is just a correlation in calculation of them.
Yeah. I was very careful in the paper and in the talk to not talk about causes, because to bring up anything to do with cause always opens you up to this type of criticism, which is totally fair. What we need to prove that this is the case is like an identifying like the mechanisms that lead to, let's say, reductions in Hessian rank. If I can't show that, I will not say anything about cause. In terms of belief, I mean, I've worked on this for some time, so of course I have like a certain degree of belief in this research program, but empirical evidence I know is only impartial. We're going to need a better theoretical understanding to really make sure that the claim is true.
Not really, like gravity.
Oh, well, we needed theory for gravity too. For now.
Maybe a follow up to that. Have you seen any problem in which your explanation doesn't hold?
Actually, in the ResNet example, it was kind of annoying to get the approximate Hessian rank to behave nicely. It's very noisy. You have 18 million parameters, and based on memory constraints, I think I can sample up to like 1,000 data points. Otherwise, I run out of memory for trying to calculate this thing. And originally, I was using 128 samples, which is great for all the other CNNs and feed-forward neural networks I was looking at. But with 128, the rank approximation had such high variance that everything was kind of overlapping. You can even see that compared to the smaller scale studies, the results were a lot more clean, less variation, whereas in the ResNet, it was higher variance. So trying to understand this phenomenon empirically at scale is becoming increasingly difficult. That's why I'm thinking we need a shift, or I need to go do a shift into theory.
Then could your approximation improve if you do like a Monte Carlo estimate, like sample really like 100 data points and then do that like 1,000 times?
Yeah, I could, but even doing it once is like, it doesn't take a minute, but it could take like 10 seconds. And then doing it 100 times is too slow for my liking. Like, but yeah, I think that could improve it. Thanks.
This is connected to that distribution shift research. Is it the exact same thing, but now you're studying it, or you're focusing on different task forces?
I'm not a lot of, I guess, research looks at distribution shifts. I guess loss of plasticity is the specific effect that a distribution shift may have on like nonlinear function approximation. Yeah, not sure. Okay, there are no other questions. Thanks.